Today we want to kind of break down how the Van de Graaff works so you understand what's going on, and then we're going to set you loose, okay? So on this little note page, if you could draw pictures and all that, and label the diagrams. I am a very bad artist, so I'm going to not draw it all out. What I'll do is I'll show you guys pictures, okay? So what's a Van de Graaff generator? Real simple. Let me show you a nice picture. In honor of this guy named Van de Graaff, we name it after him. And the Van de Graaff is a classic thing you see in science museums, which generates a lot of static charge. And if your hair doesn't have too much gel or conditioner, then the electrons will pile up and you get the classic freaky hair kind of look. So at the end of class today, we'll get a couple volunteers. And I will do my best to not let you get shocked unless you want to, okay? What's interesting, though, is this is actually really good for your hair. So anyone have a hair dryer that has an ion switch on there? Have you seen that? You flick the ion switch, and what it does is it ionizes the air, and that gets attracted to the water molecules in your hair. It actually dries your hair better, and research has shown it actually gets rid of split ends, okay? So normally a salon would charge you like $50 to give you an ion treatment for your hair. For you guys, maybe $5. It's okay. It'll be free with your subscription to physics, okay? In the old film Ghostbusters, I don't know if you saw the original one, towards the end of the movie, like the main lady gets possessed by some demon or whatever, her hair freaks out. They didn't use computer graphics back then. They didn't have the technology. They just charged up with a Van de Graaff there. That's what we're going to do. So anyway, how does the Van de Graaff work? Let's take a look here. I got a little diagram. So this looks all complicated, but here are the main parts, okay? The Van de Graaff, first of all, consists of a big metal dome, okay? Why metal? Metal is a good what? Conductor, exactly, okay? So we're going to use a metal dome because the electrons can move freely. Notice its shape, okay? Its shape is the ideal shape to distribute charge evenly. Which shape would that be? A nice sphere, exactly, okay? Because charges, do like charges like each other, or do they repel? They repel. So if you have a nice circular shape, the charges will distribute evenly, okay? Sharp, pointy things, the charges will crowd on the end of that sharp point and leak off there. So later on, I'm going to have a volunteer. I'm actually going to give you a steak knife, and you're going to point it at a student. But I labeled it physics because one year, like, hall monitor came in or the dean's office. It was a little awkward because one kid's got a knife pointing at another kid like, ah! So put the knife down, step away from the Van de Graaff. But all we're going to do is we're going to spray charges, okay? By the way, when they paint things like your car, if you want a nice paint job, a common thing to do is you use a electrostatically charged paint sprayer. You charge up the paint, and then you charge up the car opposite so that the paint sticks evenly. You get a nice finish, you don't waste paint and all that there. There was a nice little learning module that kind of showed you the applications of electrostatics, one of the absorbed physics ones. But anyhow, then, okay, we're going to charge this thing up big time because there's a motor, okay? And this was just like our cheesy rabbit fur and plastic, but on steroids. If you recall, things that have a atomic structure that tend to be more woolly, hairy, furry, felty, etc., they like to give away electrons. Plasticky things like to grab it, okay? So what it is instead of just rubbing a little piece of rabbit fur on plastic, okay, Van de Graaff had the idea to mechanize it, okay? And I think the old ones you actually turn with a crank. So there's a wool or felt roller and a plastic belt, okay? And as this plastic or rubber belt rolls across this bottom woolly, felty roller, it strips away the electrons and transfers it up here where there's these metal collector points. Sharp, pointy things like to grab charge or leak charge and transfer to the outer dome. Let me show you guys a photo of that, what that looks like here, okay? And don't worry, I'll flip back here. So inside there's a motor, and it turns the, motor-driven belt there. Hold on a second. So this woolly, felty roller likes to lose electrons. On top, there's a plastic roller. It likes to grab the electrons. Then there's a sharp metal knife edge, or sometimes there's like these sharp points that'll grab the charge and transfer it to the dome. It's as simple as that. So all it is it's charging by friction as the rubber belt rips across that felt roller, and then it charge transfers by contact because it's touching, right, the plastic roller, and then there's a little bit of inductive charge as it transfers over to the outer metal shell there, okay? You get a little bit of polarization, but in the end, it's really contact. You're directly transferring the charge. So the goal is you want to pile up a ton of electric charge on the outside there, okay? So actually, we just answered not only the first question, but the second one, why we have a round shape. Because the goal is to accumulate a lot of charge. Versus sharp, pointy things, the charges don't like each other. They would distribute as far as possible, and the electric field lines crowd around the points there. So the charges would tend to leak off there, okay? Next, 3, 4, and 5. We're going to actually kind of do in the back there. But let me show you what the magic wand is, okay? I invented this. All this is it comes with a little cheesy one that I don't use because it's like so tiny you get zapped all the time, okay? So I used to do all sorts of crazy electricity experiments, like zap myself with a Tesla, stand on top of Van de Graaff. And then one year, I charged up the Leyden jar, which you're going to see in a second. Actually, it was my first year teaching. There we go. And all the directions say, don't do this with your students. Very dangerous. Blah, blah, blah. I'm like, whatever. Charge the thing up, and then discharge it. Boom! Into just myself. Okay? So it's not a class with 10 students, 20 students. Our records, actually, we have 2 classes. And then we got Miss Joanne to join in. But I was a little worried about her because I thought, she's a little bit older. And she's like, you call me old? I'm like, sorry. And she was fine. Okay? But anyway, boom! And I'm like, mommy. So since then, I've been scarred, okay? But anyhow, now I have what I call the wuss stick, okay? Notice the magic wand consists of a wooden meter stick. What's wood? A good what? Insulator. Then I literally just duct tape on some foil and like a big wire, okay? What do you know about foil? It's a good what? Conductor. And what it is, I made my own lightning rod. That's all it is, okay? So I can safely discharge the Van de Graaff generator, and then I either plug it into the 3rd prong of the wall, because that's a ground wire, or in this case, I'm just going to duct tape it to the sink. That actually works better. What's cool is when we kill the lights, you might actually see it sparking into the sink there. Okay? Every once in a while, if it's one of our volunteers is sparking it and discharging, you'll see it actually spark through their shoes into the ground, which is kind of cool too. Okay? Excellent. So that's the magic wand. How about number 4? Why would a person's hair fly out? Think about it, right? Why would your hair go all crazy there? There you go. That's an awesome one. Captain Caveman look there, right? Think about it. If the electrons pile up on the dome, they're going to transfer then onto what? By contact, by conduction, onto the person, right? And then eventually, do electrons like electrons? They don't, right? So what's cool is your hair can be a way to see electric fields. Isn't that cool? I think that's cool. Okay? And then you could stand on the ground, but then the electrons will just drain off your body. Remember that little Brainiac clip on the electric fence there, right? So you just want to stand then on something that's what? Conductor on an insulator. On a insulated platform, right? We'll wait for the lunch bell. There we go. There we go. So I actually have a wooden platform we'll have a volunteer stand on. Okay? So how can you not get shocked? It's real simple. You will not get shocked if there's not a big voltage difference. So the trick is you're going to start off, whoever's volunteering, holding onto the Van de Graaff so as the charge builds up slowly, you won't get shocked. Okay? Then usually when we're done, I turn off the Van de Graaff, I count to 10, then I have the person let go, I discharge it, and then I have the person step down slowly so the charge slowly dissipates there. Okay? So people who don't like to get shocked, if you volunteer, I can't guarantee you 100% you won't get shocked, but I will do my darndest. And I'm about 90% there. Okay? So too much talk.